Welcome, and thanks for joining us today. If you've ever designed a wireless product, you know the antenna rarely gets the attention it deserves until something goes wrong. A device that looks great on paper underperforms in the field. Certification fails, the board goes back for another spin, the launch slips. The truth is, reliable wireless performance isn't determined by the antenna component alone. It's determined by every decision made around it: where it sits on the PCB, how the matching network is designed, how the enclosure and battery interact with the RF behavior, and whether the team validated any of it before hitting the certification lab. When redesigns are called for, the costs add up quickly. Today's webcast tackles that problem directly. We're going to walk through the full antenna integration journey with Sifiso Gambahaya, Director of Engineering at Ignion. With more than 20 years of RF and antenna experience spanning commercial and defense applications, and time spent working across 4 continents with companies including Ericsson, CommScope, and Qorvo. Sifiso brings both the depth and the global perspective this topic demands. I'm Matt Kroll, founder and principal at Chalmers Street Consulting, where we help companies find new ways to continuously improve. I'm your host today. Hi, Sifiso. Thanks for joining us.
Thanks, Matt. I look forward to this discussion, and thanks for having me.
Excellent. Let's dig in. Is antenna integration a common late-stage problem in wireless product development? And why do you think so?
Matt, that's one of the things that we find from our customers. Antennas typically come last because, let's face it, when you're designing a wireless product, you care about your application and so forth, whether it's a sensor. And at the end of the day, wireless communications comes last. And oftentimes it's too late at that point. So part of the reason is because you don't really appreciate just how important it is to design an RF system that works for that particular application. So, when they come late into the game, it's often too late, and they have to redo the entire design from scratch. And that's where, we want to come in to mitigate that before they get to that stage.
So with that, how should engineers approach antenna selection and design?
Right. So the way you look at it is typically for whatever application it is, you got to look at it from a radio perspective, right? So the radio that you choose, will, be for a certain application, for a certain wireless protocol. And from there, you can then choose the type of antenna, and this makes all the difference. So you got to look at it more from that perspective. You start with the wireless, side of things, where you talk about the radio, and then you talk about the choice of antenna for whatever wireless protocol it is, and have the antenna as the first component that you want to integrate on that PCB.
Got it. Got it. What are the most common PCB layout and placement mistakes?
There are so many mistakes that we encounter when our customers are trying to integrate antennas onto their PCB. But just for the purposes of this conversation, I'll just probably limit that to 4 or 5. The most common ones are not placing the antenna in the correct position on the PCB, which actually affects the ability to match the antenna and the ability for that PCB to radiate correctly. Or they have poor stack up in terms of the layers, and just not in the correct order. And one of the things that would advocate is to have your reference ground plane as the second layer, in a 4-layer PCB stack up, for instance, because you actually want a low impedance path for the return currents to flow through, and that way you maintain proper grounding and the integrity of your transmission line. And then other things that we encounter is very little antenna to metal clearance. They have components hovering over the antenna or very close to the antenna, which only serve to detune the antenna, and consequently also reduce the radiation efficiency of the antenna, as an example. Then you got other cases where just poor grounding practices, where you don't via stitch the board sufficiently. And then again, you've got those current loops that act as antennas. And at the end of the day, you've got an EMI problem. And that is, literally some, interference caused by spurious emissions on the board. So, these are invariably some of the things that we come across when our customers are, designing, antennas onto a PCB. Sometimes you have split ground planes, which are also can act like slot antennas, or in some cases also, cause, poor EMI control on the board.
Wow, that sounds like there's a ton of factors there that
There
you have to be
is.
aware of. I would think things like materials that you're using as well are a component of potential mistakes and that sort of thing.
Absolutely. The sort of materials that you use are important. You can also look at even the housing that you're using. Housing that are doped with metal are not good for RF. They cause all kinds of issues in terms of propagation, in terms of matching the antenna itself, inside the device. And depending on what the application is also, you might find that, the substrate or the carrier PCB that you're using, it's got certain loss characteristics that are not suitable for that particular high frequency application. So all those things do matter.
Does full device simulation change the outcome versus reference designs or bare bone assumptions?
Yeah, so typically you start from a full design simulation, and then later on, you extrapolate that to a reference design as an example, or the first prototype. It's a guideline basically. But one of the things that we encounter when you're moving from an electromagnetic simulation to an environment where now you need to incorporate all the active components in electronics, you can't really simulate thermal noise, from an electromagnetic simulator. And what you then need to do is do what we do call co-design. But that's a step too far. But some of those things you can't predict immediately, and you only get to find out the effects of that once you have the live board. And some of those effects are thermal noise, from electromagnetic interference and so forth. And you need to find ways to mitigate that. So it's not always a one-to-one translation, but a simulation gives you a proper guideline on how to get from point A to point B.
A good simulation tells you things you learn. It doesn't tell you everything. That's what I'm taking from what you're
That
saying.
is correct. It doesn't tell you everything, especially once you start looking at the layout issues that can arise, that were probably not considered, from an early stage of the design. But once you follow the proper, design sort of like fundamentals, from proof of concept, the proper Gerber review, that captures some of those things we talked about earlier, the layout issues, right? That could actually come back to haunt your design. Once that is taken care of, typically you do find a pretty close correlation between a full device simulation and also what you're getting in your first prototype.
What should engineers look for during Gerber review before sending boards to manufacture?
Right. So engineers, before they send boards to manufacture, should look at some of those things we talked about earlier, making sure that your via stitching density, is correct, for proper grounding of all the layers, on your PCB. For instance, you want to make sure that your transmission line is designed correctly. You want to have a 50 ohm transmission line and it's referenced to your ground plane correctly. So you want to check the impedance of that transmission line to make sure that it's 50 ohms. And there's several, calculators that are available for that, activity, where you can verify that, the width of the transmission line is correct. The gaps between the ground plane and the transmission line, is correct for that 50 ohm integrity. And then, look at stuff like, do we have split ground planes? And if we do, that's going to affect our performance adversely, right? So all of those things, a whole array of these things need to be looked at before you, go to manufacture. And only when all of that is corrected and done right, then do you go to manufacture.
For prototypes, how do you validate if tuning and matching are good enough?
Well, yeah, that's a very good question. And you always need a baseline. So of course, the baseline will start with the simulation as usual. And you base what you get in the lab once you do some measurements, you compare that against the simulation. The first thing you do is look at antenna impedance. You know, that's what engineers, RF engineers call S11 or VSWR. And then you see if that, more or less tallies with what you got when you do your simulation. And then the next thing you do is you look at the total efficiency. In order to do that, you measure the device radiation characteristics in an anechoic chamber. And if that, matches or is very close to what you got in your simulation, this is a good starting point for you to proceed so that you have almost certainty that once you move from design to qualification, which is the certification stage, you are going to hit it on the mark the very first time.
Um, uh, how can pre-certification reduce those risks?
So pre-certification is very important because, when we're certifying customer devices, we're not certifying the antenna. There's no such thing as certifying an antenna, but there's such a thing as certifying the device. So here we're looking at performance of the device as a whole. And there's a couple of metrics: total radiated power and total isotropic sensitivity, that govern these certification requirements according to CTIA and PTCRB or even carrier requirements. So what we do at Ignion, we walk you through that journey because we have a pre-certification service that we offer, and essentially based on the design and all our recommendations and our fine tuning that we carry out, we're able to make sure that you hit the correct TRP and TIS numbers in order for you to, get certification once you go to the, final certification laboratory for a fraction of the cost, because these tests are very expensive. And, if you don't hit the mark the first time, you have to pay a large amount on the second time around. And there's typically no guarantee unless you get it right the first time.
Interesting, and I might have, I wanted to ask, what are the biggest causes of certification delays?
Yeah, so what we've seen is one of the biggest causes of certification delay, and this comes across the whole time, is typically what we call radiated spurious emissions. And these are characteristics of the active electronics of the board typically, and they cause harmonics that interfere with the sensitivity of the radios at hand. And when this happens, it causes what we call desense, which is desensitizing the radio. And, in a real life deployment, that comes across as poor connection, drop calls, and retransmissions, draining batteries, and so forth. Just poor, very poor performance. And typically, if you don't hit those certain numbers, they're going to fail your qualification because they know how that, sort of like transpires in a real life experience, quality of service for the end customer. So radius spurious emissions is one of the biggest problems. And, our job is to then find out what those, the causes of those are and how to mitigate that, so that the device can pass certification on first go.
And this is what makes pre-certification so crucial.
This is what makes pre-certification so crucial, because if you're not able to hit the correct TIS numbers, then you're just going to fail, and you can't launch your product, and no network is going to allow you to get onto their cellular network, as an example, because they already know that you're just going to cause noise on the network, and that's not good.
Makes sense. If a team lacks in-house RF expertise, does this model help teams move faster?
Absolutely, because at the end of the day, some of the issues, let's say some of the reasons for having poor total isotropic sensitivity, or in this case, because of the RSC issues, are very complex. And you need a trained engineer with years of experience and the right equipment, in order to be able to identify and then also find ways to mitigate. Sometimes, when you get a design really late in the game, you might find that it's an absolute nightmare to correct some of this, because you have to do a complete tear down of the device, and look at it from a layer stack up point of view. So from a design perspective, you have to kind of redo the design, and that's not what you want at that point. So once you have walked through the various stages of design from proof of concept to Gerber review, design, and qualification in the proper manner, you should be able to, not go through some of these, painful bottlenecks.
Also makes sense. Do multi-radio devices create extra antenna integration challenges?
Yes, multi-radio devices certainly create, antenna integration challenges as a whole, because with multi-radio devices, when you have more than one transmitter, when you have multiple transmitters and a couple of receivers, you do suffer from interference, invariably. And one of the common ones would be integrating a cellular transmitter with a GNSS receiver. And typically those cellular transmissions, cause radiated spurious emissions, right? They cause descents on the GNSS radio. So what you want to do is you want to design very carefully how you place the antennas. You want to isolate those radios and ensure that they don't impact on each other's performance. And this is one of the more difficult elements of what we call radio coexistence. But at Ignion, we're equipped to deal with those sort of situations. We have years of experience in handling those sort of situations.
I imagine there's interactions, and those can be really hard to model and predict. Can you
Correct.
give some examples?
Right. So one of the things that we do encounter is when you have really tiny PCBs, and you've got, a large cellular antenna, right next to, a GNSS antenna, and cellular transmits at about 23 dBm power, for instance. And if you look at GNSS, the maximum power before saturation is in the order of about 5 dBm. So you want to be able to have at least 30 dB isolation. Now, it's very difficult to achieve if only you're looking at the passive isolation between the antennas, which means the radiation characteristics. You have to do something more. So you have a pre-selection SAW filter as an example in the path of the GNSS receiver, which gives you further isolation that you require in order to maintain that coexistence between the radios. But there's several techniques, not just that alone, that we use, for instance, to mitigate some of these effects.
Very good. If an engineer can leave, or if an engineer leaves this webcast with one lesson to apply immediately, what should it be?
Yeah. So for me, it sounds cliche, but it is what it is. So for us, we're always advocating for the antenna first, because once you start with your communication system, everything else follows. It's very difficult to correct the RF aspects of any design once you have, let's say, finished the design, and you look at that as, sort of like the last step in your design. Oftentimes you have to redo the whole thing again. So I would say, engage with Ignion early at proof of concept phase, and we can walk you through the journey. And we do have tools that our customers can use, such as our Ignion tool, our web-based tool that you can start with initially, but you still need a qualified antenna or RF engineer to guide you through the rest of the journey.
Excellent. Thank you for joining us today, Safiso. That was really informative and gave our engineering viewership a lot to think about. Is there anything that you want to add?
No, this has been really great, Matthew. I am looking forward to any responses from the customers or any questions that they might have, and we're here to help. Thank you a lot.
Now, stay tuned for this from Ignion.